This is the third section of chapter 5, dynamics, and this section is on simple harmonic motion. So before we get into any diagrams and equations, let's just understand what simple harmonic motion is. Well, for shorthand, we just use S.H.M, simple harmonic motion, rather than writing out simple harmonic motion all the time. And simple harmonic motion is an oscillating moment, maybe a side to side or up and down movement, about a center point, which we normally call O. The size of this motion is known as its amplitude. So the size of this oscillating motion, side to side or up and down, is known as the amplitude. And the time taken for one complete cycle of motion to take place is known as the period. So as I said, simple harmonic motion can be a side-to-side motion like this. So you can maybe like think of a pendulum or something like this. So this side-to-side motion just continues exactly the same for an infinite amount of time. Or it can be an up and down motion like this. So maybe imagine sort of a float on waves, and it goes up and down. As the waves go up and down, and again it's just carrying on in the same way. Now if we use x to represent the displacement of a particle with simple harmonic motion, either horizontally or vertically, then in the center position, then the value of x would be zero displacement, either horizontally or vertically. And what we find in the center position, this is where we find the maximum velocity when x equals 0. And also at this point, if we've got a maximum velocity, that means the acceleration in this center position is also 0. Now if we add on the acceleration, these arrows, you can see that the acceleration is always directed towards the origin. So if you've got a particle here, simple harmonic motion, then when it's on this side going towards the center, the acceleration is directed towards the center. Then at the very center, the acceleration is 0, and then it flips, and then the acceleration is now directed towards the center as it moves the other way. So it's always in the opposite direction to which the particle is moving. So the direction of the particle and its acceleration are always in opposite directions, whether that's up and down or side to side. So this gives us our first equation here for the acceleration, which is negative omega squared. We'll talk about omega in a moment and how we find out and what that's linked to, times by x. So x is going to be the displacement. So we can use this to find the acceleration. And if a particle has simple harmonic motion, then it will have an equation of this form. So if we need to show that a particle has simple harmonic motion, then we're looking to see if we can derive an equation of this form. One other point to sort of tell you about is that when we get to these endpoints here of the motion of simple harmonic motion, then the velocity is at its maximum. So it's at its sorry, it's not its maximum, don't know what I'm talking about. Sorry, at these endpoints here, the velocity is 0. So when we get to the endpoints here in simple harmonic motions, the velocity is 0. So it's maximum at the center, so it's slowing down, it gets to 0, and then it changes direction, increases speed to a maximum at the center, decreases until it gets to the other end, and then we're at 0 again before it changes direction. So at these endpoints, the velocity is going to be 0. Right, next two equations here. So if you want to find a velocity, or the velocity squared is equal to omega squared, so that omega appears again. We'll talk about that in a moment. And yeah, omega squared gets times by the amplitude of the oscillation. Now this is not the acceleration. So the amplitude of the acceleration, let's say from this center point that this moves 4 meters this way, then back 4 meters back to the center, and then 4 meters this way. So the maximum displacement from the center of oscillation is the amplitude. So that would go in here, so the amplitude squared. So if it was 4 meters this way, back 4 meters, 4 meters that way, and back to that end, the amplitude would be 4. And then I guess the total displacement from one end to the other, when the velocity is 0, that would be 8 in total, but the amplitude would be 4. And then x, well, that's just the displacement from the origin, from our center position of oscillation. Now this is where omega comes in, the period of motion. Okay, so this is the time it takes a particle to go from one end to the other and then back to where it started, so one full cycle. So if I start here, let's say 0 seconds, and I go all across here, and that takes, let's say, 3 seconds to get there and then 3 seconds to get back, then the period of motion, that would be 6 seconds. So sometimes we need to work out the period of motion, sometimes we're given a period of motion, and then we can use that to work out omega, and then omega can be put into either one of these equations here. Okay, so let's quickly go through the 3 different types of simple harmonic motion. So I've got the graphs of the simple harmonic motion, and here basically this is just showing maybe the motion. This could be horizontal as well. Right, so when I have simple harmonic motion like this that starts at the origin, so this is when t equals 0, and then it moves up and then down, up and then down like that, but it starts at the origin. Then you can see, obviously you can't see time on this, you can just see it moving up and down, but imagine as you go across in time, then you basically get the graph of sine, and the displacement of the particle can be modelled by x. The displacement is equal to a, which is the amplitude of the simple harmonic motion, times by the sine of omega t. Now because we know the period of motion is 2 pi over omega, then I'm just going to put a couple of main points on here. So after one cycle, this will be 2 pi over omega, half a cycle pi over omega. Okay, let's move on to the second type of harmonic motion, where you start at the maximum amplitude. So this would be 0 in terms of time. So you start here, you move through the origin, then to the other point of maximum amplitude, and so on. And as I go across in time, this would plot this type of graph, which is the graph of cos. So the displacement can be modelled by a, the amplitude, basically the height of the cosine graph, times by the cos of omega t. This has a period of 2 pi over omega, so that would be the time that it takes to get back to this point here, and half of the oscillation would be pi over omega. So just like the last one, I've just put these 2 points in. Then for the last one, this is an oscillation that starts at some other point, so it doesn't start at the origin, the center of oscillation, and it doesn't start at either one of these endpoints. It's somewhere in between. So we'll possibly have a graph something like this. So it's not starting at maximum amplitude, it's not starting at the center, so some other position, and this can be modeled by the displacement is equal to a, so again the amplitude times by the sine of omega t plus alpha, and alpha we get from where the motion starts, so it's starting displacement, and that is alpha over omega. So if, for example, this had an amplitude of 4 and this started at a position of 3, then 3 is what would equal alpha over omega. And once I know omega, I can use that to find out alpha and then put that in here. Okay, so this motion is for when we start at a point other than the center of oscillation, or one of these points here, or this point here of maximum amplitude. Okay, example 10. A particle is moving along a straight line with simple harmonic motion. The amplitude of the motion is 0.8 meters. It passes through the centre of origin O with speed 2 meters per second, and there are a few things we need to calculate. So I'm going to start by drawing out like a little diagram and marking on these important bits of information for the simple harmonic motion. Okay, so here's my diagram, centre of oscillation here. These 2 points here are at a distance of 0.8 meters from the centre of oscillation, and when the particle passes through the origin, its speed is 2 meters per second. So in part A, what I need to do is to calculate the period of oscillation. Now, the formula for the period of oscillation, let's write this down, is equal to 2 pi over omega. So we need to find omega, and the way that we can use that is we can use the equation v squared equals omega squared times by a squared, the amplitude squared, minus the displacement squared. And we have all of this information in the question. We're going to use this point here where we know the velocity. So the velocity squared is going to be 2 squared. Omega squared, that's what we need to find. The amplitude is 0.8, so that'd be 0.8 squared, minus the displacement squared. Now, its velocity is 2 at the centre of oscillation, so the displacement is 0, so 0 squared. So we'll use that to find omega. So omega squared will be 0.2 squared divided by 0.8 squared, leaving omega is equal to 5 over 2. So now we have omega, we can use that to find the period of oscillation, because that's going to be equal to 2 pi divided by 5 over 2, and we'll simplify that, and that gives us 4 pi over 5, and it needs to be in seconds because this is a time, this period of oscillation. So that means that takes 4 pi over 5 seconds to start wherever it starts, move across, and then come back to its starting point again. Part B, the speed of the particle when it is 0.4 meters from O. So that means we have a displacement, x is 0.4, and we can use that in our v squared equals omega squared, a squared minus a squared. So we just substitute in v squared is equal to omega. Now we worked out omega, didn't we? Let's just highlight that. There we go. Omega was 5 over 2. So that's 5 over 2 all squared times by the amplitude, which is 0.8 squared, minus the displacement, which we're given is 0.4 squared. And that will give v squared equals 3, so v equals root 3, or if we want to give that answer to 3 significant figures, let's put the units in. So root 3 meters per second, or in 3 significant figures, let's do the SD button. I get 1.7320500808, so that will be 1.73 SF, and again that's meters per second. Okay, let's move on to the next part, part C. The time the particle takes to travel 0.4 meters from the origin, or the centre of oscillation. Right, so since we want to find the time it takes to travel a displacement of 0.4 from the centre of oscillation, we'll say that when the displacement equals 0, let time equal 0. That's going to be easier, because then whatever value of t we work out, that is basically going to be the answer. And if that's the case, if it's starting at the centre of oscillation, then our model is going to be that the displacement x is equal to a, the amplitude, times by the sine of omega times by t. So we now substitute in our values. The displacement x is 0.4, the amplitude is 0.8, sine, and then omega, we worked out that was 5/2 t, and then it's just about solving this equation. So the sine of 5/2 t is going to equal to 0.4 divided by 0.8, which is a half. Then we'll do the sine inverse to both sides. So sine inverse of a half is equal to 5/2 t. That means that 5/2 t is equal to pi over 6. So we can then find the value of t by dividing both sides by 5/2, and you'll get pi over 15 seconds. Again, if we want to give the answer to 3 significant figures, I suppose I could have given the answer to a in 3 significant figures as well. That would be 0.209. It's like 2094, so 0.209 seconds. So either one of those. I think probably what I will do for the remaining questions is give exact solutions, unless the question asks specifically for a rounded or decimal answer. Example 11. A particle P of mass 0.5 kg is moving along a straight line. At time t seconds, the distance of P from a fixed point O on the line is x meters. The force acting on P has magnitude 10x and acts in the direction PO. So let's start with a diagram. So I've got my diagram. I've just stated here that if P is moving with simple harmonic motion, then its acceleration will be given by negative omega squared x. So this is what I want to try and get to. So since I've got a force, I'm going to start with F equals ma. I'm going to take the direction to the right as positive. So using F equals ma, I will have the force, which will be negative 10x, is equal to the mass of the particle, which is 0.5 kg, times by its acceleration, which I'll write as x double dot. Now I can rearrange that equation. So I now have x double dot, the acceleration is going to be equal to negative 10x divided by 0.5, or I could times both sides by 2, so that gives me negative 20x. And I can see that this equation is of this form here, so I can put, so P moves with simple harmonic motion where, and I want to match up the omega, where omega squared is equal to 20, so that means that omega is equal to 2 root 5. So I need to show it's in the right format, which it is, and state the value of the constant as well. Part B asks us to find the period of the motion. So period of motion is equal to 2 pi over omega. So we have omega, so it's going to be 2 pi over 2 root 5. 2 root 5, then the 2's cancel out. So I'll just end up with pi over root 5. That's going to be seconds. So I'll just highlight that and then go on to the next example. Example 12. A particle is moving in a straight line with simple harmonic motion. Its maximum acceleration is 12 meters per second and its maximum speed is 4 meters per second. Let's start with a diagram. So I've put on the information about the velocity, its maximum velocity. Now that always occurs at the center of oscillation, and the maximum acceleration always occurs at the endpoints here, because at those points the velocity is 0 at those two endpoints there. So the ends at the maximum minimums of the oscillation, and so I'll put down that the size of that, the amplitude, is A. So in part A I want to work out the period of motion. So the period is given by 2 pi over omega. Now I need to find omega first to find that. So the other equation that's got omega in it is v squared is equal to omega squared a squared minus x squared. So where do I know the velocity and the displacement? Well, I know it here. So at the origin we have x is equal to 0, 0 displacement, and v is equal to 4. I'll substitute those in. 4 squared is equal to omega squared a squared minus 0 squared. So that will give me omega squared a squared is 4 squared. So that means that omega a is 4. Try that down. Omega a is 4. So I've now got omega is equal to 4 over a. Let me just highlight that, because that's probably going to be useful in a moment. Now I've been told that it's moving with simple harmonic motion, so since we have simple harmonic motion, that means I can use the acceleration is equal to negative omega squared x. Now is there somewhere where I know the acceleration and I know x, because I now have got an expression for omega? Yes, at the endpoints here. Okay, so at max displacement, basically when it's moved by its amplitude, what we have here is the acceleration is equal to 12, and we also have that x is going to equal a. So we'll substitute those in along with the omega that we got before, 4 over a. So we'll have 12 is equal to negative, and then it's going to be 4 over a all squared, that's omega, times by a, that's x. So that will give me negative 16 over a squared times by a is equal to 12. So that a squared is going to cancel out with that a. So I now have 16 over a is equal to 12. So I can now calculate a, the amplitude. And I mustn't forget my negative as well. So a is equal to negative 16 over 12, which is going to simplify down to minus 4 over 3. So what I've got here is basically this over this side, so at the other end it's going to be 4 over 3. So I'll just write that down, that I'm using an amplitude of 4 over 3. I want a positive number in my working. And actually if I were to use this equation here, it will become positive anyway. So I'm using this one. So now I can work out omega. So omega is 4 divided by A, 4 divided by 4 over 3. So omega equals 3, so it's all like a puzzle that falls into place. Now I can find the period, which is 2 pi over omega, and omega is 3. So it's 2 pi over 3 seconds. Part B, we need to work out the amplitude of the motion. Now we've already worked that out, haven't we? 4 over 3, so we don't need to do any further working. That makes things nice and easy. So that means we can move on to part C. I guess this should be meters here. Yeah, so part C, what it's asking for, the length of time during one complete oscillation that the particle is within 1/3 of a meter of the centre of oscillation. Okay, I'm going to try illustrate this on a sine graph here and on my original diagram. So I know that the amplitude is 4/3. So let's say 1/3 is here and 1/3 is here. So they're both 1/3 meter either side. And what I want to do is to try and work out how long, for what length of time it's in this area. So as it oscillates from one side to the other, I need to work out, right, the time it starts here and the time it leaves there, and I want this time in the middle. That will be the time it's within 1/3. So if we take the centre of oscillation as its starting position, and we have a sine graph, if I then mark on the points where the displacement is 1/3, now remember this graph goes up to 4/3 at the top and down to -1/3 at 4/3 at the bottom. So be careful, it's tempting to put 1 and -1, but actually the amplitude of this is 4/3. So we're looking for the point where it moves 1/3 this way, 1/3 down there. So let's just mark on where these lines go. They're going to be something like this. And then I can see what I'm looking for. So during one oscillation, it's going to be within 1/3 of the centre of oscillation at different points. So try and highlight it. So this point here, these points here, and this point here. So all of these points here that are highlighted in green is when the particle is within 1/3 of the centre of oscillation. So what I need to do next is basically to work out what these values of t are, and then I can use that to find the total time. Now, since all of these times, these little bits here are all going to be the same, let's label them up. So 1, 2, 3, 4, they're all the same size. If I can work out one of them, I'm just going to times my answer by 4. So basically what I'm working out is basically the size of one of these here. Yeah, so a complete oscillation, it's going to have, let's say it goes this way, so one of those, 2, 3, 4, oh sorry, 2, 3, and then back again to where it started, 4. So I'll do that again. So 1, 2, 3, 4. So I'm using the model that the displacement x is equal to a sine omega t. Displacement is going to be 1/3, a is 4/3, sine, and omega is 3, so 3t. So it's just about solving this equation. So from here, times both sides by 3, so I'll get 4 sine 3t is equal to 1. Divide both sides by 4, so sine 3t is equal to 1/4. Let's move up here, we've got a bit of space. So now I'll do the sine inverse of a quarter, and that is what 3t is equal to. So 3t will equal 0.2526, and it carries on. I'll use the exact value. So t, I'll divide that by 3, and that's 0.0842, and it carries on. So the time that it's in within a third of that, I need to times that by 4. And let's do that, and I'll get 0.33. Now it's 69, so that'd be 7. So 0.337 seconds. That's 3 significant figures. Example 13. A small rowing boat is floating on the surface of the sea, tied to a pier. The boat moves up and down in a vertical line and can be modelled as a particle moving with simple harmonic motion. So we know what equations we can use. The boat takes 2 seconds to travel directly from its highest point, which is 3 meters below the pier, to its lowest point. The maximum speed of the boat is 3 meters per second. Let's start with our diagram. Okay, so hopefully this diagram shows what's going on. So here's a pier, and this is the sea down here. It's sort of going up and down, there are waves going up and down. This is the boat, and this is its oscillation. So that will be its lowest point here, that will be its highest point here, and that highest point is 3 meters below where the pier is. We know that its maximum speed is 3 meters per second, so that's going to be its speed at its center of oscillation, and we're told the time it takes to get from its highest point to its lowest point. It takes 2 seconds. So part A, what we need to do is to find the amplitude of the motion. So we'll find the amplitude by using v squared equals omega squared a squared minus x squared. Okay, well, at the center of oscillation, the displacement is 0 and the velocity is 3, so we'll substitute those values in. So we'll have 3 squared is equal to omega squared a squared minus 0 squared. Now we also need to find omega, and to find omega we need the period of oscillation. Now if it takes 2 seconds basically to do half of its oscillation, remember full oscillation is when it returns to its starting point, then a full oscillation is going to be 4 seconds. So the period is 4 seconds, and we know that 2 pi over omega is the oscillation, that's 4. So from there we can find omega, and that's 2 pi over 4, which simplifies to pi over 2. So now our omega can be stuck into our equation. So we've got 3 squared equals pi over 2 all squared a squared minus 0 squared. So that will give us pi squared over 4 a squared is equal to 3 squared. So a squared is equal to 3 squared divided by pi squared over 4. So that becomes a squared is equal to 36 over pi squared. So that'll give us a value of a as 6 over pi meters. Okay, so there's our amplitude. And part B, it says we need to find the time taken for the boat to rise from its lowest point to a point 5 meters below the pier. So this is its lowest point. Then a point that is 5 meters below the pier is going to be another 2 meters from its highest amplitude or highest point. Okay, so here's my diagram situation here. Now, since I want to find the time taken for the boat to rise from its lowest point, I think it just makes it a bit easier if I take t equals 0 as the lowest point and use this as my model. Now, if I want it to rise to a point which is 5 meters below the pier, which is actually 2 meters below its highest point, if you actually do 2 or 6 over pi minus 2, it's a negative number, so that should be up to this point here. So this point here would be 5 meters below pier, so 5 meters below pier at that point. And the way that we work that out is it's 6 over pi minus 2. That's what its value is there. So probably my diagram here needs to change, because that 2 meter point below the top of oscillation is actually going to be below that center point, so it's going to be somewhere down here. So I know this isn't accurate or to scale or anything, but it just gives you a better idea. And I want to find the time it takes to get from the bottom to the top here. So if I highlight it, I want to find the time it takes to move that distance. So on my diagram, it's going to be the time that it takes to move this distance here. So what I need to do now is to find a model for this. Now, if it was flipped the other way up, so if my graph looked like this, then it would be the cosine. Now, to get that to turn into the red line that I've drawn, we just need to flip it in the x-axis, which means if I just put a minus in front of my whole model, that works. I could say the displacement is equal to negative a cos omega t. If there were no negative there, then it would be the other way up. So that flips it around. I think that makes my work a little bit easier. So my displacement value of x, this point down here, is 6 over pi minus 2 is equal to negative, the amplitude is 6 over pi, and it's the cosine, and omega is pi over 2 t. Right, so all we need to do is to solve for t. So if I work out the left hand side and divide it by negative 6 over pi, I'll get 0.047119, it carries on. That's equal to the cosine of pi over 2t. We'll do the cos inverse of both sides so we can work out what pi over 2t is equal to. So that'll just be the cos inverse of what I've got on the left, and that gives me 1.52358 and so on. So now I can find t, and I just divide that number by pi over 2, and I'll get 0.969941. That's one I want to give to 3 significant figures. So t is equal to 0. Now what would that be? 970 seconds. That's 3 significant figures. So that's the time it takes to go from the bottom up to this point, which is 2 meters below its highest point of oscillation, which is actually 5 meters below where the pier is. Example 14. The particle P is moving with simple harmonic motion along a straight line. The centre of oscillation is the point O. The amplitude is 0.6 meters and the period is 8 seconds. The points A and B are points on the line of P's motion and are on opposite sides of O. The distance OA is 0.5 meters and OB is 0.1 meters. Calculate the time taken by P to move directly from A to B. Right, let's start with some diagrams. Okay, so this represents the simple harmonic motion. Let's say we're starting at O here, and it's going to take 8 seconds to do 1 full cycle. We have this point A, which is 0.5 meters away from the center of oscillation, and B, which is 0.1 meters on the other side here, and we know that the amplitude is 0.6 meters. Now what I want to do is transfer this onto a sine graph so I can then work out what equations I need to solve to find T, and then I can answer this question here about the time taken. Okay, so let's say we start from this center of oscillation here, and I was going to the right, then I'm going to have something like this. Okay, so this represents going from the center of oscillation towards the end part here, past B, 0.6, and then return again. So I can see that that's the 0.6. Point B is just going to be 0.1 meters. So I'm going to put 0.1 here, and finding this value of T here is going to be one part of my solution. Okay, so that's basically where point B is, at that displacement 0.1 meters. Now it does say we want the time taken for it to move directly from A to B. Now that's important because there are two ways we can get from A to B. We can go directly from A to B like this, or we could go indirectly. You could go A to the end of the oscillation and then back towards B, but that wouldn't be direct. So what we need to do, because this is a center of oscillation here and we've gone forward by 0.1 that way, we actually need to go backwards by 0.5. So actually we need to extend this sine graph back this way, and we're going back before we get to the 0.6 displacement, we're going back to 0.5. So I'm going to put 0.5 here, so that's 0.5, and or minus 0.5, and I need to find this value here. And then once we've found these two values of T, then the difference between them is going to be the time taken to get from A to B. So this is basically the point A. Oops, A. I said A and I wrote B. What's that all about? A. So this is the direct way from A to B. Now we get to A again when we go all the way down here, but that's not direct because this would be to the end of oscillation, back, and then, oh actually at that point we would reach A again, but this is the most direct route. That's just going straight from here to here. So I've put here the way we're going to model this. The displacement is going to be equal to the amplitude times the sine of omega t. Right, so let's write down what we've got. So the amplitude A is 0.6. The period is equal to 8, and that's going to be equal to 2 pi over omega. So we can work out what omega is. 2 pi over 8, which simplifies to pi over 4. So let's start by working out at what time the particle is at A, point A. So using our model, we have a displacement here of minus 0.5, so negative 0.5 is equal to our amplitude 0.6 times the sine of omega t, so that's pi over 4 t. So we want to solve this to find t. So we'll have sine pi over 4t is going to be equal to negative 0.5 divided by 0.6, so that's negative 5 over 6. We'll do the sine inverse of both sides to get what pi over 4t is equal to, and that's negative 0.9851 and so on. So t, the value of t, the time when t is at 8, is going to be this number divided by pi over 4, and that's going to be negative 1.25428 and so on. So I know this is a negative time. I mean, I could have gone over here. It doesn't matter actually about the numbers whether they're positive or negative. It's going to be the same time whether I use this part or this part, as long as I work out the difference between the two. Right, so I now want to work out the time when the particle is at point B. That's when we've got a displacement of 0.1. So you've got 0.1 is equal to 0.6 sine pi over 4t. So that means that sine pi over 4t is going to equal to 0.1 divided by 0.6, which is 1 over 6. So from there we can find pi over 4t by doing the sine inverse of 1/6, and that's 0.1674 and so on. So we'll work out the value of t by dividing that number by pi over 4. Just doing that on the calculator now, and that gives me 0.2132 and so on. So let's call the first time t sub a and this one t sub b. So the time between these two is just the difference between those two times, so I could call it t sub b minus t sub a, which is the 0.2132 number minus the negative 1.25428 number. And if I do that using the exact values, I get 1.46748. I want to give that to 3 significant figures, so we'll call that 1.47 seconds, and that's 3 significant figures, so we'll just highlight that answer there. So you should now be able to complete exercise 5C on pages 191 to 193. So this is the first page of recap, which we did right at the beginning, and second page of recap.